Hello everyone and welcome to Moxa's webinar, The Internet of Things Meets Big Data. Is your network prepared? I'm Martin McHugh and I'll be your moderator today. If you have any questions at any time during the webinar, please use the questions pane by simply typing in your question and clicking send. At the end of the presentation, we will do a Q&A session and take as many questions as we have time for. We'll follow up with any unanswered questions after the webinar. All right, let's get started. We'll have 30 to 40 minutes of presentation with 10 to 15 minutes of Q&A. Today's presenter is Nick Sandoval. Nick is a field application engineer here at Moxa and holds numerous networking certifications, including CCNA, CCENT, LPIC, and CCNP. So, needless to say, he's extremely knowledgeable when it comes to networking. And with that, I will hand it over to Nick.
Thank you, Martin. As Martin mentioned, my name is Nick Sandoval, and it's a pleasure to be here with you guys today. So we're talking about best practices for big bandwidth networks. So this is today's agenda. We're going to start with converged networks, then the trends and best practices. So without further ado, let's go into converged networks. So what is a converged network first? That is a solid question. Network convergence is the efficient coexistence of multiple data types on a single network. So it's grabbing a bunch of different data types, whether that's video, whether that's control, whatnot, put it onto one network. So why would you do that? Well, it offers convenience and flexibility that won't be possible with separate network infrastructures. And also, by just using one network infrastructure, you can also leverage economies of scale. As opposed to purchasing 2 or 3 or 4 different network devices, now you can just purchase one, maybe a little bit more robust, more feature set, or feature-rich, more ports, whatnot. But you can purchase less of it. So you get to leverage economies of scale. So with that, let's talk about Internet of Things. So Internet of Things is great. It's a topic that you probably hear of quite often, and this slide does a good job sort of explaining it. Internet of Things essentially is about a lot of different devices all on the cloud, on the Internet. That could be your car, that could be a camera, that could be a bike, maybe even a rubber ducky, or maybe not a rubber ducky, but that just gives you an idea. It's really putting a lot of devices all on the Internet. So I like using my house as an example. For those that know me, I'm into home automation. So what I have in my house, I have all my light switches, for example, all on the Internet of Things, all on the cloud. So that's a thing, right? All my light switches around the house, I can control it through my smartphone and whatnot. I also have my thermostat on the Internet of Things on the cloud. I also have even video streams. I could see a video from anyone coming into the house. I have even my fountain. So why would I do that? Well, first, the convenience factor of just having one device control everything. My smartphone can control my lights, my curtains, my fountain, whatnot. I have timers that turn on the fountain once a day, for example, to make sure the water's flowing, things like that. The light outside on the porch light turns on at dawn, turns off at dusk. So that's one of the convenience factors. So how's this pertinent to you? I'm not trying to get you to go into home automation, but this just gives you an idea how Internet of Things sort of works. So let's talk about industrial Internet of Things, which is going to be a lot more pertinent, I think. And it's definitely a hot topic. You see it in Forbes. It's talking about how it's important. You see articles about how GE is definitely focusing on it, as well as articles even from O'Reilly Radar. And this is just a small snippet of all the traction that Internet of Things is generating. So the question is, what is Internet of Things as it relates to the industrial space? And what does it do? So the main purpose of Internet of Things in the industrial space is that it helps build smart systems. And it does it 3 different ways, with sensors, connectivity, people, and process. So let's start with sensors. And you may ask this solid question, and this is not new, and in many ways it isn't, especially in the industrial space. We've been ahead of the curve of Internet of Things for many years in many ways. So in the sensor space, you have position sensors, proximity sensors, leak sensors, flow meters, whatnot. This forms the digital nervous system of the industrial network. How is this relevant? Well, in our space, we've been having this for a very long time, right? But really, what's been have been changing with the advent of connectivity. Now we have connectivity that's standardizing, putting LANs, putting WANs even, all on a standard-based network. For example, LAN is your Ethernet, your standard Ethernet-based network. Your switches, your routers, even your Wi-Fi, all falls into the LAN space, and that's all standards-based now. Where in the past it wasn't; it was mainly serial. Wide area network is the internet. We even have cellular connectivity that could put things right onto the internet. But having connectivity and having all the sensors is useless if you don't have the right people and processes aligned, right? At the end of the day, you want people to be able to look at useful data. That's where processes really fall in play. You have to have all these processes gathering all this data and make it meaningful for people. So now that we talked about Internet of Things, and that's really talking about increasing device count, what it comes down to, right? And the common trend is that it's going to increase device count by 10-fold to what it is today. But what happens when you increase device count? You increase data points. As you increase data points, what does that do? More data means you have big data, right? You have a lot of data now, which is going to lead to big bandwidth, the purpose of our presentation. So Wipro came out with this excellent slide here that talks about how big data is shown in the industry, and we have this presentation from both Wipro and Gartner. So one thing that's important to note is, what is big data? So Wikipedia tells you that big data is a collection of data sets so large and complex that it becomes difficult to process using on-hand database management tools or traditional data process applications. So think about it. You're grabbing all these sensor data, and we have to make it meaningful, right? As you increase this amount of data, it's impossible for people to be able to process all this. So you need to have complex processes to be able to do that. Now what's interesting to note is, if you look at that world map in the very top, in the United States it's 3,500 petabytes of data. That's more than the entire, I said the United States, North America. That's more than the entire world combined. So that's huge. So we're really in the forefront when it comes to big data and the Internet of Things. And what's also interesting to note is, in the very bottom left-hand corner there, they actually had a survey where only 57.6 organizations said that they were ready for the big data challenge. But let's focus on that Gartner graph, the big data investment by industries. So Gartner came out with this question that they asked a bunch of different organizations across the North America. Has your organization already been invested, or is your organization investing in technology specifically designed to address the big data challenge? Green meaning yes, the dark blue being don't know. Now, there's three different questions on the no side which are interesting. The first being no within a year, that's orange. Gray being within 2 years, and the light blue being no time soon, or no plans at current time. And now if you look at these three different focus points here, is that this is an industrial space: transportation, energy, utilities, and manufacturing. Now, if you take together, yes, they're already ready, and no, they're not, but within the first year or two, it's a great majority. So most of our industries are looking at addressing the big data challenge, which at the same time is going to address Internet of Things. So that's going to lead to our poll question. So the poll question is, do you currently build your network to take account Internet of Things and or big data? The first question is, not yet, but you're considering it. Second, you're only looking at Internet of Things. Third, you're only looking at big data. D, oh, absolutely. Or the honest answer, no, right? All right, the poll questions are coming in. I'm seeing a good majority was saying absolutely, and it's actually shifting. But you are considering, great. So now the majority is saying that they are considering it. So, okay, Everybody make sure you dial in there. We're almost done here, getting a lot of great data. So the one leading the way is not yet, but considering it, but no is also there. Okay, so that's the results we're seeing. A good majority are saying no, but not considering it. Another good majority is also almost equal, saying no, but we have a lot of people saying absolutely. So what is the trends we see in the industrial space? So right now we're seeing a paradigm shift in networking. In the beginning was legacy and device networks. Many of you have this today perhaps, or are already in stage 2. Legacy device networking is a one-to-many type of application, one-to-N. You have serial to Ethernet gateway, so you still have all these sensors on the network, but using gateways usually, as opposed to them having network connectivity from the start. You're using a lot of field protocols out there, Modbus RTU, Modbus ASCII, DF1, sorry, Profibus, and many others, right? It's a different type of network, usually separate from the rest of the network space, and it's mainly reliant on data and command structures. Now, this is where we're definitely today in most spaces. You have the pervasive industrial network. It's a many-to-many application. Now you have devices that actually have network connectivity from the start. They still use field bus technologies, but now it's the network versions. It's an IP, Modbus TCP, Profinet, for example. But the difference about this type of network is that these are standalone networks. You have your own network for data and control usually, a different network for voice and video and voice. Your factory floor is a different network than you have in the control center or IT space. And the shift we're seeing today is a converged automation network. So we talked about the converged networks in the past, right? In the beginning, it's that network where we're putting a lot of different network types all into one. So this is a one-net approach where field bus protocols are not as prevalent as they were in the past because you have devices that natively support IP from the start. So that leads us to this type of network. This is a quad play network. You may have heard of that. And what quad play really means is that you have a network that's converged with voice, data, video, and control. And you can see all that being represented here with your controllers like PLCs and whatnot, I/O, HMIs even. You have even a camera. And you even have a VoIP, a video over IP phone solution here. And this is another representation of how this is seen in industry many times. Now, what's interesting here, and we'll get into this, but this is sort of an edge-to-core approach where you have two different tiers on your network, all connecting a bunch of different devices, including wireless, including your device layer, where all your sensors are and so on. Then you have your control layer, and then you have more your core layer. With a lot of redundancy built in, and in the core layer you have your network management software, your surveillance system, even your SCADA server. That's where usually it's going to reside. So let's talk about best practices. Granny always says, do this. So first, when you build a good-sized network, you want to build in 3 different tiers: the edge, distribution, and core. So your edge are the devices that usually are going to be connecting to your end devices. So the edge connects to your distribution network. Usually distribution is going to have redundancy. It's going to be much faster than your edge. Your edge you get by with just fast Ethernet, for example. Your distribution, you're almost always going to have gig. Sometimes faster, sometimes you get away with fast Ethernet if you don't have much traffic, but usually it's going to be gig. And the core, this is the beefiest part of the network. Again, you have redundancy built in this layer, but now you're talking about 10 gigs and so on. So obviously it's not going to be this simple. On a distribution layer, you can have a lot of devices usually connected to it. A lot of different subsets. It could be industrial PoE switches, it could be substation level switches, it could be M12 level switches that have vibration-proof connectors and can even be waterproof. And the edge layer is comprised of more than just standard switches. You could have media converters, you could have wireless here, and we can't forget the device level, the field networking, your Ethernet to serial gateways, and whatnot, as well as where security is going to really reside on. Security is really going to reside on edge, not so much on distribution and less so on core. By the time data gets to core, the expectation is that security is handled on the edge. But I'm not going to go into security into great detail. So one thing that you need to note, though, is it's great having this network, but if you can't really manage it, if you can't see how the status of the network is at any point in time, it's going to be a challenge to make sure that's working effectively. So you definitely need to have your industrial management software. That's an important point. So a good way of seeing it is sort of like a tiered approach, where your edge is definitely going to be your largest, distribution less so, core being the smallest but the fastest. Now, is all your networks going to be built in three tiers like this? Not necessarily. It depends on the size of your network. If you're talking about a smaller network, usually you're going to get by with just an edge and distribution, and you don't need the core layer, and that'd be fine. You still normally want to have network management software there. That's always a good practice, is to have that a solution to sort of monitor your network and make sure you know the status and the health of your network. And if there's any issues, it could alert you to that. Now that's going to lead us to quality of service. This is probably one of the most misunderstood best practices, I would argue, which we're going to ask the pull question. So the question is a quality of service metric, what is the quality of service metric you use to design your network? Or do you use quality of service when you design your network? It could be not really, don't, yes, you absolutely do, or the only metric you use is a ruler. Alrighty, so right now a lean pack is absolutely, not really being second place. Third place is the only metric you use is a ruler, and that's a interesting one, right? I use rulers for everything. Alrighty, so lean pack was definitely absolutely. That's great to hear, actually. So what is quality of service? So quality of service could be abbreviated as QoS, and many of you probably heard QoS. So quality of service is not a protocol. Quality of service is the overall performance of a network above all the perceived performance seen by the users. Perceived performance being key. So it's sort of like going to checkbox. You know, what are you going to rate the network performance, and what level does the network performance need to be? It's not going to always be outstanding, right? It's going to depend on your requirements and your network requirements, and we'll talk a little bit about that. So one of the first things when it comes to quality of service is determinism. So determinism is a deterministic system in which there's no randomness that's involved in the future states of the system. So determinism means that you need to be able to predict the delay and be able to build out your system knowing exactly when things are going to occur. So this is huge in the manufacturing space, right? And process control, where you need to know exactly when things are going to occur. Think of things flowing by fast and robots grabbing things and sorting, things like that. So you need that to be very deterministic for everything to communicate together, right? So determinism helps measure, quality service helps determinism. So industrial applications require it. Determinism is very important in the industrial sector. There are industrial protocols out there like Ethernet IP that require it, actually built into the spec, that it depends on the network being very deterministic. Network failure in a lot of these environments can be very costly, and that's one thing that you need to see when you determine what the quality of service on your network is what is the total cost of downtime. For example, the total cost of downtime could be loss of production, right? That's one of the obvious ones, the opportunity cost. But it's more than just that. And that cost could be significant, 10,000s to hundreds of thousands on a lot of manufacturing per minute. But it's also the cost of figuring out whatever issue you have whenever there's downtime, is the cost of loss of confidence on your customers and whatnot. So those are things you want to play in when you determine what your quality of service is, how much you can invest in your network and things like that. So what are the metrics you use in quality of service? What are the parameters? There are three primary: delay, jitter, and reliability. So delay is an easy one, right? It's how long it takes you to get from point A to point B. So this is actually a common site here in California. We're actually located in the LA Orange County area. So traffic jams, a common site. That's obviously going to create a lot more delay than if the roads were wide open, right? So what is jitter? So when I talk about jitter, I'm not talking about the jitter you get when you drink a whole lot of coffee or before you actually present a webinar to a large audience. That's not the jitter I'm talking about. Jitter is actually the variance in delay. Let me explain. Let's take into account, let's use the example, rather, of when I commute to work. It takes me about 20 minutes when there's no traffic. When there's heavy traffic, worst case scenario, it'll take me 50 minutes to get to work. So that jitter is from the 20 to 50 minutes. So if I want to get to work on time, then I have to take into account this jitter and what the traffic flow is. So that's where jitter becomes an important parameter. And obviously reliability, you want the system to be have high uptime and so on, and how reliable the system needs to be depends again on you doing your metrics on what quality of service is and so on. Now, reliability is important that it's across the board, right? If you have the weakest link in your chain there, that's going to be the lowest point of reliability. So what are the three different methodologies that we apply quality of service? That's predictive, flow-based, and class-based quality. Predictive uses over-provisioning. Flow-based, I'm not going to go into much detail because nobody uses it. It's used a little bit in the commercial sector, but even then, it's not something you're going to see very much. Class-based is used quite a bit. But by far, the most popular is predictive quality. So let's get into it. So predictive quality is like having that glass ball, the crystal ball, that you could see the future. So you need to be able to see the future and the present to be able to really do this. You have to build out your network. What is my future demand? What is my current demand? And build out for it. The premise is that if you have no congestion, will packets get through? Think of this scenario. Hopefully everybody's been to the airport where you see two different lines, high priority line, low priority line. You see this in amusement parks. You see this in a lot of other types of avenues as well, where you can either pay more to go to high priority line or you have a certain status to go to the high priority line, right? So with predictive quality, the premise is have no lines to start with the use of over-provisioning. If you have no lines to start with, does it really matter whether you go to the high priority line or the low priority line? It does not, right? It's the exact same thing. You get from point A to point B at the same time if there's never a line. That's what over-provisioning helps do. Over-provisioning means you provision a lot more resources than you need. The more over-provisioning, the more of this you're going to get, right? Where there's no lines to speak of, which is going to eliminate jitter. So in the commercial space, and I'll let you think of this for a second, what do you think is a percentage that they usually quote by? You know, when you want to build networks to have this amount of bandwidth for a good network that's going to be fairly reliable. That percentage is 70%. So when you go to any network training, they train you to build out your network for 70%. In the industrial space, it's a whole lot lower than that. 70% is not going to cut it. And it depends on your level of determinism and how mission critical your application is. For example, in the nuclear industry, when I deal with these customers, usually they're going to be building out their networks from 5 to 10. So their network is only going to be utilized from 5 to 10% at any one given point of time. So that way they have it like this. You always have a whole lot of space. And their data is getting through without any lines, without any queuing. When you go to areas that are less mission critical in the industrial space, usually I see the tops being about 20%. So it's from 5 to 20% really where networks are built with over-provisioning. So keep that in mind. So next let's talk about class-based. So class-based is saying, okay, when there is a line, let's prioritize. Similar to my example before, right? I had a low priority, no priority. So, but you can have different levels of priority levels. In this case, we have 3 different traffic flows trying to leave all one port, getting there at the same time. Which one's going to get out first? It's going to be the top priority, which is our control traffic in this case. The messaging traffic being a little bit lower priority, lowest priority being the data, so that's going out last. So this is class-based using QoS protocols. So this is where protocols really come in play. So with predictive, there's no protocols used whatsoever. With class-based, there is. And what's important to note is you can use both at the same time, right? You could have it so that, hey, let's try to eliminate the lines to begin with, but when there is lines, let's make sure we have the traffic that's the highest priority get out there first. So here's another example, right? I talked about check-in at an airline. What about when you actually board? There's also priorities there too, right? Boarding groups 1 and 2 usually go first. 3, 4, 5. The higher the number, the lowest priority you get. The later you're going to board the plane. How usually it works. So how class-based is it? It's node level. So once you leave in this area, when you get to the plane, there's a big line there. It doesn't matter what priority you were. You could be priority 1, and if there's already a big line there and it mixes for whatever reason, it doesn't matter what your priority levels are. It all gets mixed. We actually board inside the plane. There's no longer any control of that priority levels, right? So class-based is node level. It only happens at that device. So from switch to switch, if you want to have effective quality of service using class-based quality, you have to make sure that every device supports it. Otherwise, you have a bottleneck. So the advantage of this, too, is highly scalable, though, because you don't have to have any management of the whole network to be able to do class-based. It's node level. It's done at every single switch. So it's very easy to scale up. Just make sure that the additional devices you add, whether switches or routers, support it. Now, there are downsides, though. First, no standardization. What that means is there's multiple protocols out there, and even on the protocols, there's no rule, or should I say there's no law that defines exactly how certain traffic flows have to be highest priority or low priority. There is rule recommendations, but not every manufacturer has to support it. Now, for the most part, you'll be okay mixing manufacturers, but when you start mixing too much, there are some that may not follow the standardization, so you have to keep that in mind. You may have to go in there and make sure that the quality of service parameters align. You may have to reconfigure that. So the con then being 2 things. One, a bunch of different protocols. There's TOS, type of service, class of service, differential services, all different protocols. And there's you may have multiple being used all at the same time. And everyone has to follow the rules on how these protocols, when they say high priority, whether that's really going to be high priority or not. Next question is going to be multicast. Now, we did have a poll question here, but because of the technical services difficulties we're experiencing, we're not going to go through the actual poll question, but I will prompt it up for you. So the question was, are you using Internet IP, video, voice in your network? And the response is yes, not yet, but plan on it. Only on Ethernet IP or no media plans. So if any of you answered A, B, or C, then the next section is going to be very relevant. Even if you did not answer no media plans, definitely pay attention though, because maybe it's more important than you realize. So let's first talk about what is multicast. So multicast is actually a new form of Ethernet communication compared to unicast and broadcast. Unicast is a one-to-one conversation. If I was just talking to one of you and no one else is really hearing me, that's a unicast conversation. One-to-one relationship. Broadcast is one to everyone, sort of like the format here, right? Everyone gets to hear me. Not everyone might be listening to me, but everyone's at least hearing me. That's a broadcast. You get to hear me whether you want to or not. What I have to say may not be of interest to you, but you have your speaker on, so you're hearing me. So that's a broadcast. These devices get the message whether they need it or not. Multicast is saying, you know what, I'm only going to send a message to the ones that really want it, the ones that are asking for it. That's multicast. So it's one to several, and it's select several. So let's talk about the advantages and why I have multicast to begin with. It's going to lower the amount of traffic on the network, which is going to mean better bandwidth utilization. So in big bandwidth environments, we want to lower the bandwidth utilization a little bit, right? So that we don't have to have as many. Maybe you could get by with a gig traffic as opposed to going with 10 gig if you didn't have multicast. It's going to do less processing, and it's also going to control when you're going to have the traffic going to select receivers. So one thing to note, though, is that multicast is great when you have a single producer sending the data to multiple consumers. Yeah, or you have a single device that's generating the traffic, send it to devices that want to receive that traffic flow. That's where multicast becomes powerful. So what is a multicast advantage? Now this example is with audio traffic. Now it's a very linear relationship. As you increase the number of clients, if you were to do this with unicast, you would increase the number of traffic significantly, right? Now this example is only with 8 kilobit audio, so the example would actually be much higher if you include video, for example. So with multicast, though, you can see that no matter what the number of clients there is, the multicast stream is the exact same thing. It's only one single stream. That stream is being managed to a bunch of devices, not like a bunch of different streams being generated. So for the end device, it's a lot less work, right? It just has to create a single stream. It doesn't have to create a bunch of different streams for a bunch of different devices. So that's a lot less processing on that device. So one thing with multicast, though, is it is protocol-based. You do need to have a smart network to support it, and that's very important. So you don't want to do this if you have unmanaged switches, for example. That's definitely a no-no. Frankly, unmanaged switches is usually a no-no in my book. Internet Group Management Protocol is a protocol that's used heavily. It's a layer 3 protocol, so this is something you can have more on the layer 3 network infrastructure, whether it's layer 3 switches or routers. End devices must support the protocol to really be useful. So if your device doesn't really support it, there might be no advantage to it. Most video encoders, for example, are going to support it. Most voice over IP, like voice phones, are going to support it. So for the most part, if you're using a voice or video, you're already set. Ethernet IP, for example, supports it. That's one of the few entry protocols that supports multicast natively. And you actually want to use it. If you use Ethernet IP, definitely want to be using multicast. Now, for network infrastructure, layer 2 specifically, they don't support IGMP natively. They support IGMP snooping, so keep that in mind. You want to make sure that's on if you're going to be using multicast. That's really what's going to help you take advantage of having the multicast filtering. Now, the other best practice is to do network segmentation, and usually you're going to be doing this with layer 3. So what is layer 3? We go to this model called the Open System Interconnect model, sort of where the name came from. So the very bottom layer is the physical. The second layer up is data, and the third layer is our layer 3, being the network layer. So that's where the name comes from. When we hear layer 3 switches, you're doing this in layer 3 and whatnot, it all comes from here. And there's several different types of layer 3 devices, routers, namely, and layer 3 switches. So what's the difference between the two? And that's a question that is very common, and it's a good one. So one thing to keep in mind, a layer 3 switch is going to be much faster than a router. Even if you have the fastest industrial router out there, it's still not going to be a match to the layer 3 switch. Like a good example I like to use is if you had a fast industrial router, like Moxa has an EDR GNL3, and you put a layer 3 switch next to it, and let's put that into terms like cars and things like that. Let's say that layer 3 switch, that router, sorry, is a Bugatti Veyron. For those that know what that is, that's a $2 million car or 1,000 horsepower, fastest production car out there. Fast as heck, right? But a layer 3 switch, if you were to compare that to a vehicle, I'll make that a fighter jet. It's just going to be much faster. No comparison. One reason why it's so fast is that a layer 3 switch does everything in hardware, where a router has to process everything on software. So everything has to go to the CPU. As you're doing things in hardware, you can do things in parallel. You could do all these kind of things all at the same time. Every port could be routing at the same time. So that allows you to have higher port densities. So you can see layer 3 switches usually have a lot more ports than routers. A layer 3 switch usually can be VLAN based. Routers are usually interface based, but that is not a rule written in stone. There are routers that are VLAN based as well. And a lot of the software features you're usually not going to see on a layer 3 switch. A lot of that is, think about this fighter jet, and if you, that's hardware based, and that's why it's performing so fast. But if you put all these software features, it's sort of grabbing this fighter jet and putting it down on the road, right? As opposed to the sky. It's just not going to go as fast. You're not going to take advantage of its capabilities. So a lot of times you're not going to see layer 3 switches have VPNs, network address translation especially, firewalls, another thing you're not going to see. They have some similar features resembling some of these, but they usually don't have full features that you're going to see on routers. So then the question is, okay, so we talked about all these devices, we sort of know the differences between them, but why use them, right? So let's talk about the benefits, and then we'll talk about the deal scenario next. So the benefit of having layer 3 is to improve performance in large networks. It also increases security. Network segmentation in general increases security because, especially if you bridge it with layer 3, because if you're in one segment, you can't cross to the other segment unless you allow them to. So that also helps control traffic, which also allows to bridge different segments together using layer 3. Like when you have VLANs in there, you know you're going to have layer 3 switch almost if you need to have these VLANs talk to each other. So the deal scenario. So a small network may not need layer 3, but if you have a large installation or big bandwidth and big data type of networks usually require, then this would be an ideal scenario. You definitely are going to have layer 3 in these type of networks. Whenever you need segregation or isolation, when you need to segment the network or isolate, for example, you may have a network segmentation like a control network you don't want anyone else to have access to, but it's all part of this converged network, then layer 3 could definitely help create rules and so on so that only certain devices could talk to that network segment. Need for security. I sort of already gave a great example of that, is how we isolated the network and so on, control who has access to it. With routers, we could have firewalls and whatnot. When network address translation is needed, and I didn't talk much about network address translation, that's sort of a topic in itself in many ways, but whenever you're going to be connecting to the internet, for example, you're going to be using network address translation quite heavily. So know that if you're going to connect your network to the internet, you're going to be using NATing. So you're going to need to have a firewall, router/firewall device there. The firewall more for security. Network address translation is handled by the router, and interfacing with the WAN. The WAN being a wide area network again, which is like the internet. So now, let me give you an example. It said performance. It helps improve performance, but how is that really applicable? So there's something called the broadcast domain. Now, picture me in a room. I'm speaking out, right? Everyone that hears me is in my broadcast domain. So another example is everybody in this webinar is in the broadcast domain. You guys are all hearing me. So if there's one person speaking, not a big deal, right? In this example, we have 15 devices, and one device is broadcasting out. 14 devices get those packets, whether they want to or not. But when we scale that up, we see that there's going to be issues. Now, if we increase the number of devices on the network, so let's say we have 1,000 devices out there, and you have devices that want to all communicate together. Say you have 100 devices communicate at a time, sending broadcast messages. You have 99,900 packets being sent out now. And for those that know, broadcasts are a very common thing on a network. There's a lot of things on networking that require broadcasting even for it to work, like Address Resolution Protocol, ARP, for example. It's just one example. So it's going to happen on your network. You're going to have broadcasts. It's very difficult to control. So you don't want this large broadcast domain. So what you want to do then is segment the network out to multiple usable chunks to prevent it from being so busy. So when you break it up to multiple chunks here, that's great. Now we segment, and now we have the broadcast domain small, and within each single broadcast domain, things are very fast. Great. We need them to talk to each other almost undeniably, right? There are occasions where you want maybe A not to talk to C, but you want A to talk to B. So that's what you could do with Layer 3. Layer 3 creates the bridge between these different broadcast domains, and it can control who could talk to who and whatnot, whether that's through access control lists or firewalls or things like that. So to sum up all these topics we've been talking about, some key takeaways. So industrial networks are moving towards converged networks that require a lot of bandwidth. So keep that in mind. We talk about the quad plane network. We talk about Internet of Things, how Internet of Things is scaling up the number of devices on a network and how that's putting it all onto the cloud and whatnot, and how that's creating big data. And at the same time, we're converging all these networks to a single network, so that's going to require a lot of bandwidth capabilities. So with that, I'd like to thank everyone for attending. And we're going to take any questions you guys have.
All right. Thank you, Nick, for that. So we do have a couple questions here. So Nick, it looks like the first question we have is, do you really see industrial Internet of Things taking off? And this one comes from Chris.
Thanks, Chris. That's a great question. And we do. We definitely, and in many ways, I sort of said early on, our industry in many ways have already been adopting Internet of Things before Internet of Things even became a buzzword. We've been putting a lot of sensors, a lot of different type of data points onto networks of all kinds. So we saw that trend chart early on. We definitely do see that taking off.
Okay, great. Thank you very much, Nick. This next question is from Thomas. Thomas wants to know, of the best practices that you went over, which one is an absolute must? Is there one that sticks out?
Absolute must. That's a great one. All these are important for different parameters, and I'm going to give the consultant answer, which is it depends. It depends on what your network is and so on. But the one thing you do have to start with is quality of service and find out what your network requirements are and building out to make sure your network has the right reliability, controls delay and jitter and so on. But remember, if it's a large enough network, then Layer 3 is going to be really important. If you have a lot of video, you have a lot of things to have a single producer with a lot of consumers, multicast is going to be very important.
Okay, thanks again, Nick. This next question is from Francisco. Francisco wants to know, what are the implications for databases when it comes to keeping historical data? So what are the implications for databases when it comes to keeping historical data?
That's a very good question. So the implications, obviously, is if you have a lot more data sets, you may not be able to handle it on a single data historian, for example. You may have to have multiple if the data stream gets that big. The implications also mean you may have to have a lot more use of network technologies like NAS drives, network attached storage devices connected to these data historians. It means the requirements are slowly going to go up and up and up on where we have all these data accumulators to. Your data historian may not, what you had yesterday may not be the right one for a few years down the line. You may need something beefier down the line with a lot more storage capabilities, and you may have to go with a distributed model where you have multiple.
Perfect. All right. Thank you, Nick. It looks like the last question that we have here is from Jeffrey. Jeffrey, I guess, wants additional clarification on Layer 3 versus router, and perhaps if you can go back into the presentation and show the table that you had there. and maybe give a little bit more clarification on layer 3 versus routers.
That's a good question. So one thing that I need to note is a layer 3 switch is a router by its main function. It routes. It's going to route traffic. So a router and layer 3 switch both do the same thing. They're going to route. The difference is how they do it, and how they do it helps associate when you use it and some of its capabilities. A layer 3 switch could do its routing through hardware specifically, so it's a lot faster. A router does it through software, so it's not as fast, but software is a lot easier to define new features and do a lot more functionality than you can in hardware. It actually gets impossible to incredibly expensive to do everything in hardware. So layer 3 switches aren't going to have all the bells and whistles you're going to see on routers, like I was telling you, firewalls, for example. Layer 3 switches have access control lists that could do a lot of things that firewalls can, but aren't as powerful. So again, the difference between layer 3 switch is when you need to have high performance. Usually it's going to be throughout your network, you're going to be using a lot of layer 2 switches usually, and the router normally is only going to be connected wherever you really need security because of the firewall capabilities and so on. So for example, you definitely need a router if your network's going to touch the internet. If you're doing internet things, then that's going to be important to you. So you have the router there. The layer 3 switch is not going to be touching the internet, but if you have a lot of points you're routing to, you can have layer 3 switches as well.
Awesome. Thanks for that insight, Nick. And we did get another question in from Patrick, so I want to address that here. His question is, with Multicast, isn't performance affected by the level of responses required to the multicast messages? And he has a follow-up as well. Doesn't this need to be taken into account when planning performance?
So that's sort of a loaded question in a way, because it depends where the processing we're talking about. On the edge device, the device actually creating the messaging type, it's actually less processing for it because it has to only deal with a single stream as opposed to dealing with many streams. Now, it will cause greater processing on your network infrastructure, of course, because now the network has to manage it as opposed to not having to manage. Now, one thing I didn't mention is a multicast stream in a layer 2 network that is not being managed is treated as a broadcast. So keep that in mind. If you have multicast streaming in there, like Ethernet IP forces you to use it, you can't tell it not to, with exceptions, then you want to have multicast filtering enabled. It will put a little bit more loading on the network infrastructure, but it's going to definitely help you when it comes to bandwidth utilization.
All right, thank you, Nick, for that additional clarification and insight. So with that, we're going to conclude the presentation. So thank you, Nick, and thank you, everyone, for your interest and participation. Also, everyone will be receiving a follow-up email with both the recording and presentation slide deck. Lastly, please take a minute before logging off to fill out our survey, as we really value your input and feedback. Thanks again for tuning in, and have a great rest of the week, everyone. Thank you.